page 43. All right, we mentioned in section P4 that you are going to feel like they are throwing every type of equation on the face of the earth at you all in one section, because in essence that's what they're doing. They're reviewing all of the stuff that you have seen before. And so it's kind of a little bit of everything. And that's the case when we get to page 43. We have points of intersection of two graphs. So basically we're looking at a system of equations, right? We're going to have a whole chapter on systems of equations, chapter 7, a little later on. But if I were going to solve a system of two equations, we could do it algebraically or graphically. There are several different ways that we could do it. We've learned how to do substitution. We've learned how to graph it and find their point of intersection. We've learned how to do like an addition-subtraction method. Sometimes it's called linear combination. Sometimes it's called elimination. And the book even has an example where they set the two equations equal to each other and solve, which is very similar to substitution. So let's look at a couple of ways that we can do this with the understanding that it's just review and it's a preview of something we'll spend a lot more time on later on. When you're looking for the solution to a system, you're looking for the ordered pair that would make both of the equations true, as opposed to just the solution for one equation where it only has to work in that one. So I'm looking for the ordered pair that I could put in for x, y here and in for x, y here that would make both of those equations true. So if I'm going to solve this by the addition-subtraction method or elimination or linear combination, whatever name you want to give it, my goal is to get the coefficients of one of my variables to be opposites of each other so that when I combine them, they drop out. So if I were to multiply this top equation by a -2, that's a legal move, right? Because what you do to one side, you do to the other side. Then I would create an equivalent equation. -4x plus 6y equals 4 is equivalent to 2x minus 3y equals -2. They graph the same way. They would be equivalent lines. They would lay on top of each other. So therefore, this is called an equivalent system to this original system as well. So I haven't changed anything. So now if I go through and combine, a -4x and a +4x would combine so that the x's cancel each other out, and that was my goal. I wanted them to eliminate. 6y minus y would be 5y, and 4 and 6 would be 10. So what's y equal to? 2. So then how do I find x? Plug it back in, right? So I could take y and plug into either of those equations. I chose the one that I had not altered. The 4x minus y is equal to 6. So I can plug 2 in for y and then solve for x. So what will I get for x? 2. So the solution for my system would be 2, 2. If I went back and I put 2 in the place of this x and 2 in the place of this y, I would get -2. And if I put 2 in the place of this x and 2 in the place of this y, I would get 6. It works in both of those equations. Now, another way that we solve this really often is by graphing. But there are some downsides to graphing. It's going to take me a while, right? Because I have to graph two entirely different lines, two different XY charts. You know, it's not especially accurate unless I'm using like big block graph paper and a straight edge and being really, really precise. It's not always accurate. And if my answer here, instead of being 2, 2, if my answer is 1 7/16 2, I don't care how accurate I am on my graph paper, it's going to be really hard for me to find that precise of a solution. So that's where the graphing calculator can help me, because it speeds things up and it can give me that accuracy that I need. So if I'm going to throw this into the calculator, what do I need to do? Yeah, I got to solve them for y, because when I put them in my calculator, they have to be y equals, right? So I would go through and I would take each of those equations that we were just working with, and I would solve each of them for y, in essence putting them in like slope-intercept form since they're linear. And then I could throw them into y equals in my calculator. So let's do that. Here were those two equations that we just had, 2/3 x plus 2/3 and 4x minus 6. So type those into y1 and y2, 2/3 x plus 2/3 and 4x minus 6. If you don't have the new operating system with that math print, no problem. You just put your fractions in parentheses. So parentheses 2 divided by 3 parentheses. That's fine. Now, typically when I graph, I start with a zoom 6. You know, that's our standard all the way around. So that's probably what I would do here. I would go to a zoom 6 just to see what I get. And if I don't like it, I can always change it. So here's my zoom 6, and you know, I know my answer algebraically was 2, 2, so if I come over here, x is 2, y is 2, that looks pretty legitimate, but it would be nicer if I had a closer view. So I think I'll go back to the zoom 4, or I could always set my window by hand to be whatever I wanted. So that's a lot better where I can go over to, up to, and see that point. But again, if this answer was really 1 and 7/16, 2, I probably still wouldn't be able to see that. So my calculator can tell me what that precise point of intersection is. And the way that we do that is we go back to that same button that we've said all the best stuff is on the calculator. It's second trace, which is my calculate menu. We've talked about value. That's where you put in any x value that you want and it finds the y value for you. We've talked about 0. That's the one that finds the x-intercepts, where you give it the left boundary, the right boundary, and the guess, and it finds the x-intercepts for you. So for this one, we want to choose intersection down here. So I'm going to choose number 5. And when I do, it'll automatically position itself on what I have in y1. And it'll say, do you want me to use this for the first curve? And it has positioned itself on the graph of 2/3 x plus 2/3. So I just hit enter to tell it yes. So enter. And then it jumps over and says, do you want me to use this, y2 equals 4x minus 6? Do you want me to use this for the second curve? And I could, it's right now at 0, -6 is why I can't see it. If I just trace over a little bit, you'll see it come up on that line. So there it is, so that you can see it has positioned itself on the graph of 4x minus 6. That's what I had in y2. So it's saying, do you want me to use this for the second curve? I can tell it enter for yes. And then it's going to ask me for a guess. So I can go to about where I think that point of intersection is. Sometimes I can land right on it, sometimes I can't. In this case, I can land right on the 2, 2 and say this is my guess. And it will verify for me that that point of intersection is 2, 2. Remember that we've talked about before that intersection equals solution. Every single point on this line is there because it is a solution to that equation. Every single point on this line is there because it is a solution to that equation. So if I'm looking for the one-ordered pair that's a solution for the both of them, it would have to be that one point where they intersect. So intersection equals solution. Alright, so just a reminder of what we did. We solved each of those equations for y, because that's the only way that we can type them into our calculator. And then we put them into y1 and y2 and hit graph. We tried the zoom standard, and then we ended up going with the zoom 4, the zoom decimal. Then we went to second trace, which was our calculate menu. And we asked it to choose number 5, which was intersect. And it would go through a set of prompts where it would ask me, do you want me to use what's in y1 for your first curve? And we told it enter for yes. And then do you want me to use what's in y2 for your second curve? And we told it enter for yes. And then it asked me for a guess, so we went as close to the point of intersection as we could get and hit enter. And then it actually gave me my intersection, which was the same as the algebraic solution that we got. Okay. Now, over on the top of page 45, they talk to us about solving polynomial equations algebraically, and they give us a chart up there where it has degree, name, and example. So I kept the part of their chart that they had with the name and the degree and the example, but I've added a few extra columns to the chart that weren't there. to help us out a little bit. If we're going to be graphing all of these different polynomials, it's a good idea for us to have an idea of what they're going to look like before we start, and some components of them just make things a whole lot simpler for us. So, of course, we know that anything that has a degree of 1, like we were just working with here, x to the first, anything that has a degree of 1 graphs as a line. A degree of 2 is a quadratic, and it's going to graph as a parabola. A degree of 3 is a cubic, and it has that like sideways S shape. A degree of 4 is a quartic, and it looks like a W or an M. A degree of 5 is a quintic, and it has one of these basic shapes. Now, they don't always look that way. Sometimes we get imaginary solutions, or we get multiple roots at the same point that can alter the shape of the graph, but we're just talking about as a starting point here that those are the basic shapes of the graph. Now, let's look at these other columns that we've added in. You'll notice that the number of terms that a graph has is going to be exactly 1 more than its degree. Like we know a linear equation has a degree of 1 and it doesn't turn at all. We know a quadratic has a degree of 2 and it turns 1 time to make a parabola. But we could keep going with that same pattern here. So let's say that they gave me something that they wanted me to graph, like y is equal to I don't know, 2x to the third, and it wouldn't even really matter what came after that if it was y equals 2x to the third. So 2x to the third, and it could have anything after that that it wanted to. I'm really only interested in this first piece because that 3 tells me that it's going to turn 2 times. The other thing that we noticed in our chart is that the leading coefficient, now the leading coefficient is the number that is in front of the highest powered variable, okay? So that leading coefficient, if it's positive, it tells me that my graph will end going up, and if it's negative, it tells me that my graph will end going down. So here's the deal. I can look at this and say the leading coefficient is positive. I know my graph is going to end going up. It's a degree of 3, so according to that chart, it's going to turn 2 times. So I could say, okay, there's turn 1 time, there's turn 2 times. I have a really good idea of what that thing looks like before I plot the first point in a table. So if I have an idea of the shape of that graph before I start, I might get away with plotting 10 points instead of 20 to get just as accurate of a graph. So that's why we wanted to add in those additional components there while we're beginning our study of polynomials, as opposed to waiting a little later on so that they can be more beneficial to us now. Okay, so we want to focus on page 45 on polynomials, specifically quadratics. Quadratics. Now, we've learned quite a few different ways to solve a quadratic. We could solve it by factoring. We can solve it by completing the square. Sometimes to undo a square, we use a square root. Sometimes we use the quadratic formula. So we're just going to go through and review those different methods. So let's start with factoring. If you have a trinomial, factoring is when I'm taking that trinomial quadratic and breaking it into 2 separate binomials. So if I've got x squared, that would break down to x times x. So my first term here times my first term here has got to give me my first term here. For my last term in each of these binomials, I'm looking for what would multiply to be the negative 6, but add to be the negative 1. So what multiplies to be negative 6 and adds to be negative 1? Negative 3 and positive 2, yes. Then once I have it factored, I can set each of those factors equal to 0. Now, not everything will factor, and so that's why we need other solutions, other ways to find solutions. So for the next one, we've got x plus 3 squared is equal to 16. And we mentioned to undo a square, you can use the square root. So if by chance you have a problem where you have a perfect trinomial square, you could go through and you could take the square root of both sides. So we'll take the square root of both sides. Remember that when you insert a square root, you always insert plus or minus. And the square root and the square would undo each other. So now how do I get x by itself? subtract the 3. And I wouldn't leave it as negative 3 plus or minus 4. I would say negative 3 plus 4 to get the 1, and I would say negative 3 minus 4 to get the negative 7, and that's how I would write those two solutions. All right, completing the square. These are the steps for completing the square that we've used down here. Before you start frantically writing those down, if you look right across the page, the next page in your notes packet has these steps written with one change. Those steps were written specifically for that proof that we're going to look at tomorrow. And so in the third step, it doesn't give the formula for completing the square like I've given it to you here. It basically gives how to complete the square for that particular problem. So you may want to go over to that sheet if you are unsure of the steps for completing the square and just kind of write this out, because this is your formula that you use. Coefficient of the middle term divided by 2 squared. So you could just make yourself a little note about that one piece, and then all the rest of it would be the same.
Number 3.
Mm-hmm. Okay, so these are our steps for completing the square. Step number 1, we're going to move the constant to the right-hand side of the equation. All right, so for our problem, they already did that for us. Fantastic. Number 2, we're going to divide both sides by the leading coefficient. They were nice enough to make my leading coefficient 1 here. So if I divide everything by 1, not going to change anything. Step number 3, and here's where I actually complete the square. And here's the formula for completing the square. I'm going to take the coefficient of the middle term, divide it by 2, square it, and add that to both sides. Take the coefficient of the middle term, cut it in half, square it, and add that to both sides. So when we're looking at x squared plus 6x equals 5, here's my middle term right here, 6x, right? So what's the coefficient of that middle term? 6. So we're going to take that coefficient and we're going to cut it in half, so that would be 3. And then we're going to square that, which would be 9, and that's what we're going to add to both sides. So one more time, according to that formula, find your middle term, which we did, that was 6x. Take the coefficient, which was 6. So 6 cut in half would be 3, and 3 squared would be 9, and that's what I want to add to both sides. Now, if I have done this correctly, I will have created a perfect square on the left-hand side. A perfect square is one that when I factor it, I get the same term in each of my binomials. So, like if I factor this, I'm going to get x plus 3 times x plus 3. And I could write that as x plus 3 squared. Once I get to that stage, I am right back to where we were over here, right? Is that not the exact same kind of problem? Okay, so I could then go through and solve the same way. Insert a square root of both sides. So that's what step number 4 says. Take the square root of both sides. Don't forget your plus or minus. And then just finish solving, just like we had done in the previous example. So that's our process for completing the square. If something won't factor, and we have the option of either completing the square or doing the quadratic formula, I think 99% of us would choose the quadratic formula. Particularly after I link you the handy-dandy little program that does the quadratic formula for you. But I need to see for this test that you can factor by hand and do quadratic formula by hand, and then after that I'll give you programs that will do those things for you that we'll be able to utilize. So let's go through quadratic formula. First off, here is your quadratic formula up here. You do have to know that formula. The key for the quadratic formula is identifying a, b, and c. So if I line up ax squared plus bx plus c with my problem, what is a? 2. What's b?
3.
And what's c?
-1.
All right. So we could go through and say, now that we've defined each of those values, let's throw them into that formula. So negative b, you told me b was 3. Plus or minus the square root of b squared, so again b is 3. Minus 4 times a, which you told me was 2, times c, which you told me was -1, all over 2 times a. Alright, so here is the most common mistake with the quadratic formula. Actually, two things that are probably the most common. One is we forget to set it equal to 0 first. So if they give me a problem that looks like this, we're trying to say that C is positive 5. It's not. It would have to be subtracted over so that we're set equal to 0, and in that case it would be negative 5. So that's one thing we miss. But the most common mistake that I see with this is we start right here inside the radical and we say 3 squared is 9, minus 4 is 5, times 2 is 10, times negative 1 is negative 10. What's wrong with that? I did not follow order of operations. Order of operations says that I have to do exponents first, and then I have to do the multiplication before I can do the subtraction. So I need to multiply these to get the negative 8 first before I try subtracting that negative 8 from the 9. So as long as I follow that order of operations, then it's pretty straightforward from there. If there's any simplifying or anything that I can do at the end, I surely want to do that as well. Now, we mentioned that you have to know the quadratic formula. There is this handy-dandy little quadratic formula song. I'm going to play it for you repeatedly every day until you're walking down the hallway singing it, and you'll hate me this week, but when it comes to the test and you start humming it and you know the formula, you'll be much happier.
Try that again.
Pop goes the weasel will never be the same. All right. Last thing we want to look at is example number 8. Example number 8. All right, for example number 8, we're looking at a quartic in quadratic form. What do they mean by that? Okay, a quartic we saw on our chart earlier is something that has a degree of 4. But this is in quadratic form. What do they mean by that? So, like if we look at this quadratic up here, if you'll notice this middle variable, when you square it, you get the first variable, and then this is a constant, right? So look at this. If I take this middle variable, x squared, and I square it, I get x to the 4th, and this is a constant. That's what we mean by a quartic that is in the form of a quadratic. So if it's in the form of a quadratic, I can solve it like I would a quadratic. This might actually make it a little clearer. If you'll take that middle variable, that x squared that we were looking at, and substitute it out with something else, like I just chose y, then it makes it a little clearer for us to see how that really is in quadratic form. So if that makes it easier for you to see, then just solve that quadratic that has the y in it. Y squared would have to factor to be y times y, and what multiplies to be 2 and adds to be negative 3 would be the negative 2 and the negative 1. So factor that quadratic like normal and get your solutions. And when I get down here and I've got y is equal to 2 and y is equal to 1, then I can come back and say, okay, I put y in the place of x squared, so now let me back substitute. Let me put the x squared back in the place of each of those y's. So how do I get x by itself? Square root. And remember, when you put in a square root, you've got to put in the plus or minus. So I'm going to get a positive square root of 2, a negative square root of 2, a positive 1, and a negative 1. I'm getting 4 different solutions there, which is good because this is to the 4th power. Now, you don't have to substitute. If you look at this problem initially and you say, okay, x to the 4th, that just factors to be x squared times x squared. And what multiplies to be 2 and adds to be negative 3 is negative 2 and negative 1. You can factor that quartic into 2 quadratics. That's fine. So if I set each of those factors equal to 0, then I'll get x squared equals 2 and x squared equals 1. That's the same place I was right here. I've just gotten there a whole lot faster and easier. To get rid of the square, I would just take the square root and be sure that I put those plus or minuses in and I'd still get the exact same answer. So either way you want to go, if it's easier for you to see to substitute it out, or if you can factor it as it is and save yourself a few steps. Doesn't make any difference. Either way. Now, for your homework tonight, I want to talk to you for a second about your challenge because it's a little different than usual. For your challenge, I want you to create the quadratic formula. I know we get this idea that people sit around, eons ago and just made up random formulas for us for today, but here's where the quadratic formula comes from. If you take ax squared plus bx plus c equals 0, and you go through these steps of completing the square, you will magically create the quadratic formula. It is just ax squared plus bx plus c in a different form, is all that it is. So that is across the page in your notes. It's the very next note sheet that you have that we're going to work through tomorrow. But I want you to try it on your own first tonight as your challenge before we work through that tomorrow. Okay? And then here is the rest of your homework on pages 50 to 53.